Hello, everyone. Welcome back to our channel. Previously, we have covered several essential topics in our journey through machine learning. We began with supervised learning, where we discussed how models are trained on labeled data, allowing them to learn the relationship between features and target variables. Next, we explored linear regression, one of the simplest algorithms used in supervised learning, focusing on its objective to find the best fit line that minimizes the distance between predicted and actual values through the linear equation y equals mx plus b. We then examined the types of linear regression, differentiating between simple and multiple linear regression, which vary based on the number of predictors involved. Our discussions also included model evaluation, emphasizing the importance of assessing model performance using techniques like cross-validation and data splitting to ensure unbiased results. Additionally, we delved into the concepts of overfitting and underfitting, critical to understanding model performance. We learned how overfitting occurs when a model captures noise in the training data, while underfitting arises from a model being too simplistic to represent underlying trends. Finally, we discussed common metrics for linear regression, such as mean absolute error, MAE, mean squared error, MSE, and R squared, which help us gauge the effectiveness of our models. Now, let's take a moment to think critically about our learning. Imagine you're working on a linear regression model, and suddenly you notice that your predictions are significantly deviating from the actual outcomes. What if I told you that these discrepancies could mean the difference between a model that performs well and one that fails to deliver accurate results? So, think about this. What could these deviations imply for the overall performance of your model? How might they affect your confidence in the predictions it makes? Furthermore, what methods can we use to quantify these errors effectively so we can refine our model and enhance its predictive capabilities? This brings us to the pivotal concept of the cost function, which serves as a crucial tool in our quest for model optimization. Reflecting on the impact of errors in our model's predictions, let's explore the concept of the cost function. As we discussed in our earlier dataset of housing prices, where we used home sizes of 1,500, 2,000, 2,500, and 3,000 square feet, and corresponding prices of 300K, 400K, 500K, and 600K, we can analyze the performance of our linear regression model. In this plot, we visualize the relationship between the sizes of homes and their actual prices. The actual prices are depicted as blue points scattered across the graph, while the predicted prices from our model are represented by a red line. You'll observe that for some homes, the predicted prices closely align with the actual prices, while for others, there are noticeable deviations. This is where the cost function comes into play. The cost function quantifies how well our model's predictions align with the actual target values, serving as a crucial measure of its performance. In linear regression, the most commonly used cost function is the mean squared error, MSE. MSE formula is the average of the squared differences between the predicted values and the actual values. Specifically, we take the total number of observations, and for each observation, we find the difference between the actual value and the predicted value. We then square that difference to avoid negative values and finally compute the average of all these squared differences. By minimizing the mean squared error, we can determine the optimal parameters for our linear regression model, significantly enhancing its predictive accuracy. Let's dive into an example to demonstrate how the cost function plays a vital role in optimizing our models. We begin by importing the necessary libraries. First, we use NumPy, imported as NP, which will help us efficiently handle numerical operations, such as creating arrays for our dataset. Next, we use matplotlib.pyplot, imported as PLT, which will allow us to visualize the data on a graph. We also import the mean squared error function from the sklearn library. As we discussed in a previous session, the mean squared error function is essential for evaluating the cost function, as it calculates the error between the actual and predicted values. Now let's create our dataset. We will use the same dataset as before, with the sizes of homes, sizes as an array, 1,500, 2,000, 2,500, 3,000, and the actual prices as another array, 300, 400, 500, 600. Next, we need to define the model parameters, specifically W and B. In linear regression, the formula we use is y equals W times plus B. Here, X represents the sizes of the homes, and our target Y is the predicted prices, referred to as predicted prices. For simplicity and clarity, we'll set the intercept B equals 0 and an initial arbitrary slope W equals 2.0. Now it's time to visualize the data. We first plot the actual home prices on the graph using plt.scatter, where the sizes are on the x-axis and the actual prices on the y-axis. We'll represent the actual prices as blue points, labeled accordingly. Next, we plot the predicted prices on the same graph. To make it easier to understand, we'll add grid lines using pl.grid for clarity and then display the graph. This visual representation will help us compare how well our model's predictions align with the actual prices. Now we can observe from the graph that there is a significant difference between our model's predicted prices and the actual prices. Let's go ahead and calculate the mean squared error MSE to quantify this difference and see what value we get. The mean squared error function requires two key arguments to compute the error. The first argument is the actual prices, which represents the true values from our dataset. The second argument is the predicted prices, which are the values generated by our model based on the input features. By comparing these two sets of values, the mean squared error function calculates how far off our predictions are from the actual outcomes. This gives us a numerical measure of the model's performance. We observe that the MSE value is quite high, indicating significant error in our model's predictions. Now let's try adjusting the weight W to a lower value and recalculate the MSE. After making this adjustment, we notice the MSE has decreased but is still relatively high compared to our earlier calculation. Let's further reduce the value of W and check how the MSE changes this time. We observe that the MSE continues to decrease gradually as we lower the value of W. This indicates that we're on the right track by reducing W. Let's continue lowering W further to see its impact. Eventually, we find that the optimal value for W is approximately 0.2, where the MSE is at its lowest. For understanding purposes, we try decreasing W even more, but we notice that the MSE increases again. From this, we can conclude that when W 0.2 and B equals 0, the model's predictions are most accurate, giving us the best possible outcome. In conclusion, we've seen how adjusting the model's parameters, specifically the weight W, significantly impacts the mean squared error, MSE, and ultimately the accuracy of our predictions. By systematically lowering W, we were able to find the optimal value where the MSE was minimized, indicating that our model's predictions are most accurate when W equals 0.2 and B equals 0. This process has shown us how the cost function plays a crucial role in guiding the model towards better predictions. In our next session, we will explore gradient descent, a powerful optimization technique that automates this process of minimizing the cost function, making the model even more efficient. Gradient descent helps us fine-tune parameters like W and B to achieve the best possible results. If you found this session helpful, don't forget to like, share, and subscribe to stay updated with our upcoming lessons on machine learning.